This PowerPoint's all about technique. So we're going to run through KVP, mass, filtration, SID, generator type. And so it's all about your exposure factors. And we're going to kind of take a look at this just a little bit, and then I'm going to bring this up and we're going to take a look at the Brems spectrum, what happens whenever we change all of this stuff. If you can understand the Brems spectrum, you can understand what's going on with changes in each one of those. So what we're going to talk about is the control of beam quality and quantity, and what each one of these things, how it affects quality and quantity, quality and or quantity, because some will affect some and some will affect some, but not all the above. So we're going to talk about each one of these and how it affects the Brems spectrum. Brems spectrum is really the output of the X-ray tube as you adjust these different things, right? So it's just a visual for them. So what we get is every time we change these things, we're going to have either a change in quantity, a change in quality, or both. So we're just going to say the words, and then we'll bring this up and take a look at it graphically. So whenever we change our KVP, let's say and I'm only going to go in one direction with each one of these, right? So naturally, if I say we increase KVP, then it increases something. Then if we decrease KVP, then it decreases. Exactly. So I don't have to go in both directions with each one of these. Just know that the opposite is always going to be true. So when we increase KVP, what do we get?
Decrease numbers.
If you increase your KVP,
And that's the only thing you do. Increase KVP, you're going to
increase quality, quantity.
increase quality and quantity. Exactly. So we tend to, kind of hammer in, we increase our quality, but we also increase quantity. If you remember, a 15% change in KVP equals how much of a change in mass? It's double, right? So there's a relationship there, right? And it's direct. As we increase, but it's exponential. 15% change in KVP is equal to a doubling of the mass. So it's a direct relationship. It goes in the same direction, increase, but it's exponential. 15% equals 100%. So as we increase MA or time, either one is truly a direct relationship, right? Unless we introduce reciprocity, and reciprocity is increase one, decrease the other. But if we just increase MA or just increase time, it's going to equal an increase in mass, and that is strictly a quantity issue. It has no effect on quality at all. Remember, quality is anything that on the Brems spectrum that we're going to draw, it pushes towards the high energy side. So, the reason I'm going that way is because every time I draw the Brems spectrum, the high quality side, the high KVP side, is in that direction, right? So, increased distance. Okay, so what distance are we talking about? So make sure that you pay attention on your test question. If it's asking for an increase in distance, well, what kind of distance are we talking about? If we're talking about SID, then as we increase distance and we don't change anything else, well, our output doesn't change, right? Our output doesn't change as we increase SID unless we change something else, right? Our output remains the same. But if we're phototiming, what's going to happen? You increase distance, and what happens here?
Decreases numbers.
Well, if you don't change anything,
right,
it's going to decrease numbers striking the image receptor. The output from the X-ray tube doesn't change, but it decreases numbers striking the image receptor. But if you're phototiming, mass is naturally going to increase. Right? We took a look at that today, right? So as we increase our distance, we're going to get an increase in output. So also, though, make sure that you're not looking at a question that's asking about air gap, because with air gap, you get a increase in OID. With an increase in OID, you get a decrease in what's hitting the image receptor. And naturally, again, you need to increase your mass in order to compensate for Same thing for decrease in distance. So, decreased voltage ripple. So we have a change in voltage ripple. What are we talking about there?
Like, one phase.
Single phase, three phase, right? Three phase high frequency. So what we've got there then is, with single phase, regardless of what kind of single phase it is, we have a 100% voltage ripple. The output of the X-ray tube comes to a complete stop whenever, it makes it to the line with each one of those pulses. Even if it's rectified, it's still going to come to a stop. Any single phase, 100% voltage ripple. Three phase is going to be 14% to 3%. So we have a decrease in voltage ripple. What does that do for our quantity? Our numbers.
Should increase.
It increases, but because also our waveform never comes to a complete stop, what does it do to quality? It increases the average, so pushes it towards the high energy side. And then whenever we have filtration, we change our filtration rate. If we increase filtration, or if we have an increase in inherent filtration, I don't know if it says decrease, but I'm going with increase. If we have an increase in inherent filtration, which naturally happens because of tanning of the tube, then what happens to our tube output?
Goes down.
It decreases, but at the same time, it decreases, and what happens to our quality? It increases, right? So the things that are going to affect our quantity are going to be our KVP, our mass, be it MA or time, our distance, and that's going to necessitate a increase in tube output, voltage ripple, and decreased filtration. So your exposure factors then become KVP, MA, the prime exposure factors, KVP, MA time, and distance. And our quality issues give us changing or what we affect quality with is a change in KVP, voltage ripple, and filtration. So let's do this. Get rid of that. And do the Brems spectrum for the last time in your life. You might see it on the registry, but as far as, you're drawing it out, this will be the last time. So let's do it like this. We'll say KVP, and then we'll say mass, and we'll do filtration, machine phase. What am I missing? That's about it. Okay. All right. So let's say our original technique, let's say just, pick a technique, doesn't really matter what it is. We'll say it's 80 kVp. No, let's not say 80 kVp. Let's say 60 kVp, reasons we'll talk about here in a minute. 60 kVp at, I don't know what we're shooting here with 60 kVp and 20 mass, but it's just numbers, don't really matter, except the 60 kVp does. All right, so we've got KVP, we've got mass, we've got filtration, and we've got machine phase, right? So I'm going to, y'all know my art, right? It's really not good, but I'm going to try to make these as similar as possible. Okay, so we've got a Brems spectrum, and let's start actually with the blue, or the green, because it'll stand out a little better. So at your anode, at the face of your anode, your emission from the anode is isotropic, goes off in all different directions with equal intensity, right? And what we're most interested in is what comes through just the port, right? And it eventually goes through your collimator housing, and that becomes your primary beam. So at the collimator house, at the anode, your Brems spectrum actually looks like this. So that what you get, and it's a 60 kVp, what you get is an X-ray beam that is comprised mainly of low energy X-ray photons. Very few of your peak energies. So it looks like that, but that's not the beam that you use, right? That's just what it looks like coming off of your anode. A lot of low energy X-ray photons. I read somewhere that the lowest energy X-ray photon to still be considered an X-ray photon is in the tens of thousands of volt range, right? It's not even about a kVp yet. So we get a lot of those. We get almost none of these. We get a tremendous number of these. This area up here and any area under here represents just numbers. So we get a tremendous number of low energy X-ray photons, very few high energy X-ray photons. But what does it have to go through before it eventually makes it to the patient? What's the first thing it hits? It's coming off the anode, inside the X-ray tube. What's that?
The shutters?
The shut? Not yet.
Mirror?
Not yet. What's that?
The window?
The window is the third thing it hits. Yeah, third thing it hits. What kind of X-ray tube do we use? What do we say it is? A vacuum tube, right? So what is what holds the vacuum in? Not the oil.
What?
Glass. The glass envelope. It's a glass envelope, right? Like sound effects, did you? It's a glass envelope, right? So it goes through the glass envelope. Is glass radio parent? Ever heard the word radio parent? Not since the first semester when I told you that nothing is radio parent. You talking about that? Okay, so it's radio lucid, meaning that it's going to absorb some of these, right? So now our Brems spectrum looks like that. So I gave you a spoiler alert. What's the second thing it hits? So I said that this thing does not hold the vacuum in. That would have been you almost said it, I think. Somebody said it. Oil. Oil. So what is oil? For those of you who are not East Texan, that is oil.
Okay.
Oh my gosh.
What is it? I mean, what's it similar to? What are you made out of?
Water.
Water and
Oh, yeah.
fat. Right, we got a lot of fat. Okay, so you cook the fat down, what do you get? Oil, right. You absorb X-rays?
Yeah.
Yeah, so does oil absorb X-rays?
Mm-hmm.
It's not radio parent, it's radio lucid. So it's going to absorb some, and now your Brems spectrum looks like that. And so the third thing was, who said it? Window, bingo. The window, so it's got to get out of the housing, right? And that's out of the protective housing, which we learned earlier this semester does not protect us from as much as what I thought it did. So it goes to the housing, the port, and it looks like that. And the next thing is I think you said it, your
Shutters?
second,
Mirrors?
mirrors. The shutters don't do anything for filtration. The mirror then absorbs a little bit too. So now our Brems spectrum looks kind of like that. So this area under here represents numbers, just numbers, right? So what happened as we increased our filtration?
Decreased our lower energy?
Right, we decreased the number of low energy X-ray photons, which means our numbers go down, right? It also took out all those lowest energy X-ray photons, which means that, let's say I throw out your lowest grade this semester.
Average.
Ain't happening, but let's say I did, then our average goes up, right? So average goes up, our numbers go down, and it pushed this thing as representative of the average. So the peak of the bubble represents average. It pushed it towards the high energy side. right? So this is 60 kVp, that's 0 kVp. Okay, so it pushed towards the high energy side. We lose numbers, we increase average, pushes it towards the high energy side. Right, that's filtration. So the only thing that affects your minimum energy is this. That's it. So if you increase filtration because of tanning, you get increase in inherent filtration, your numbers are going to continue to go down. Your average continues to go up and it continues to push towards the high energy side. You get to a beam that's more homogeneous. All energy levels are more similar. Okay. So you get to a point where more tissues, or the tissues that you penetrate, are penetrated at more of the same rate. That was significant in screens and films, okay, because it could affect your contrast. I worked on a machine. This was a I'll think of it in a second. They break up kidney stones as well machine, electronic shockwave lithotripsy machine. So it breaks up kidney stones with sound waves. And in this particular machine, we used it a lot. And when I first went to work, they paid like $3 million for this thing. And this was back in, I hate to tell you when, but I graduated from program 93. And my first job was shut up. My first job was in surgery at ETMC. And they hadn't had this machine long. $3 million back then was a chunk of change. And I worked there for 2 years. And when I first got there, it's still a chunk of change, but we've got, years worth of, inflation now. So, when I first got there, you could see kidney stones well. Worked there for 2 years. And by the end of that 2 years, you couldn't see kidney stones for anything. They came in, they added software and they tweaked it and they adjusted all the stuff that they could adjust, try to bring up the contrast, and you couldn't see it. Just couldn't see it. And the only thing I can think of is that, because we use this thing so much that we lost so much contrast because our X-ray beam, we lost contrast because of added inherent filtration. Nothing else on the system had changed except for how much we used it. All right, so filtration, it affects the minimum energy. Theoretically, in a digital world, we might lose some contrast because we have a more homogeneous X-ray beam. Computer algorithm being the main thing that affects your contrast, you're probably not going to see it that much unless you really got a lot of inherent filtration. So the only thing that affects minimum, height goes down, height of the bubble goes down. If we were to add more filtration, the height of the bubble decreases as well, meaning that we lose numbers, pushes everything towards the high energy side, and our average goes up. Okay? Everybody good with filtration?
Mhm.
Any questions on filtration? Okay. Then now what I've got to do is I've got to try to reproduce that. So what do we want to do next? I'm going to save machine phase for last because it's probably the most confusing in context of filtration. So let's do KVP. So we got a funny little sharp thing right there. So that's our Brems spectrum. It's supposed to look like that one. If it doesn't to you, then it's your eyes, because my heart is perfect, right? So we're still at 60 kVp. What is it that affects the minimum energy? It's only one thing, filtration, right? So now we're going to change our kVp. So with the changing kVp, what we get is obviously we're going to move off of 60 kVp and we're going to go to now, let's say 80 kVp. Okay, so what we're going to see with a change from 60 to 80 kVp, which is massive, right? 15% change from 60 kVp would be roughly 69. I didn't go with 15% change for, what's going to be an obvious reason. But what we're going to get is our minimum energy remains the same because our minimum energy is only controlled by filtration, right? So it comes off in exactly the same spot, but we get this massive change in what's under here? Numbers, right? So numbers increase. Our peak energy increases. We went from 60 kVp to 80 kVp. I'm just going to do this because it increases so much. We get a massive change in numbers. We get a change in peak energy, right? Okay, what I say that the height of the bubble represented not just numbers, but also it represented the average. Bingo. So now our average is here. Regardless of what kVp we use, our average is roughly a third of our peak energy, right? So at 60 kVp, maybe I should make it 90. 60 kVp, our average would be 20. So let's just go ahead and do that to make it simple. Now at 90 kVp, our average is 30. So our average goes up. Push towards a high energy side, but it does one other thing, and it's the thing that controls two different things. KVP determines what your peak energy is. That's why we call it a KVP. And where were you going?
Characteristic.
Characteristic. Bingo. What we didn't have here was a characteristic spike, right? Because it exists at 69.5 kVp. Most of the time, they're just going to say 69. They don't round it up. They just say 69 kVp. Okay, so 69 kVp, it determines whether or not we have characteristic spectrum. If we're shooting at 68 kVp, we don't have one, right? If you go back around chapter 8, it discusses characteristic spectrum. You know that you create characteristic X-rays, but the only one that we record is 69. The ejection of the inner shell electron replacement with a free-floating electron gives us 69 kVp, right? So there's only one that we document. So KVP gives us our peak energy. It determines what our peak energy is. It determines whether or not we're going to have a characteristic spectrum. It increases numbers exponentially, right? And it pushes towards a high energy side. And it gives us our characteristic spectrum. So, it determines our penetration. It does all that stuff. All right. So historically, we've used KVP in technique adjustment for really only one thing, and that is if we have a pathology that increases the absorption of the X-ray beam, like if we have a patient with acromegaly, be it because of osteopetrosis or because of pituitary tumor, the bone growth, we might increase KVP. We might decrease KVP if we have a pathology that destroys bone, osteoporosis, or maybe rheumatoid arthritis, right? But aside from those, or maybe casting material or something like that, but aside from those type of disease processes or additive tissue, we always used mass, and still do always use mass as our compensation, right? So KVP, since it doesn't affect contrast anymore, I do believe that you're going to start seeing more change in KVP. And actually, I think you've seen that a little bit. Patient size, for example. If you push the button that says you're shooting a asthenic patient, and you pay attention to what it's giving you as far as KVP goes, then you push hypersthenic patient, you're probably going to see an adjustment in KVP. Right? So for KUB, let's say, for an asthenic patient, it may say 80 KVP, maybe 85 for a hypersthenic patient. So you see it a little bit, but I think it'll become more prevalent. I think it'll eventually be the technique of choice for adjustment for, patient thickness or whatever, because it just doesn't affect contrast all that much anymore. All right, so everybody good with KVP? All right, so then mass, and granted, we've got two different factors for mass. We'll get into that later on in reciprocity, but going back with our original over here, Our minimum is only affected by, that's got a plateau. That's a West Texas, Brems spectrum. So when we change mass, first off, what is amperage? It's again going all the way back to first semester physics. What is amperage?
Voltage. Or,
Voltage is voltage.
yeah.
Yeah. Okay. Voltage is the thing that pushes the amperage. So the amperage is it's just the numbers. It's count of electrons. That's all it is. All right. So milliamperage is just a smaller count of electrons. Milliamperage. All right. So what mass controls? What MA controls is the heating of the filament. So you heat the filament up, you get to the point of thermionic emissions, right? So you got all these things. You hit it with KVP and they go across the X-ray tube. And it's just a count of electrons. That's all it is. All right. So if it's just a count of electrons, how is that going to affect your peak energy? Trick question.
It won't.
Won't. Right. So what's the only thing that affects your minimum energy?
Filtration.
Filtration. So if you just increase let's say you've taken 5 tests in a semester, and you scored different scores on those, and you add another 5 tests with the exact same scores, what's your average look like? Same, right? So what is it then that mass is going to do to our Brems spectrum? Increase numbers. That's it. That's it. That's all it does is increase numbers. So what we're going to have then is we get an increase in numbers. The height of the bubble remains in the same spot. The peak energy remains the same. The only thing we get is an increase in numbers. Because it increased just numbers and nothing else, and KVP increased all this stuff, this became the adjustment factor of choice and it still is in most cases. Because you don't change the imaging characteristic of your X-ray beam in any way, then this is what has historically been the factor of choice. Again, I expect that to change some. So numbers only. The machine phase, you're going to have a tendency to confuse machine phase and filtration. You're going to have a tendency to flip them about. Okay, so with machine phase, what we're talking about is going from single phase, three phase to high frequency. And what we get then is with an X-ray beam that is, it's unrectified, single phase X-ray machine. What we get is these pulses at 60 hertz, 60 cycles per second. That's bad for the X-ray tube because we want to send electrons from cathode to anode, right? But if you remember, I know it's been over a year, I can pass them around again, but if you remember the anodes that I sent around last year, one of them was pretty badly melted, right? It had a thin layer of tungsten, but as soon as they burn up the tungsten, it got into that copper underneath. It was a stationary anode, and it just melted it to pieces, right? So if it can melt that tungsten that's covering the copper and melt the copper, and it's a big hunk of metal, then what could it do to that little bitty thin tungsten filament if the electrons were coming from anode to cathode? Same thing real quickly, right? So we don't want that to happen. So we're going to rectify, we're going to take and send 2 pulses across. Now we've doubled the output of the X-ray tube. That's still single phase. We still come to a stop every single time. 3 phase is where we send 3 different sets of pulses out of sync with each other. So it kind of spackles in that, gap. You know what spackle is, right? You got a hole in the wall where you hung a picture, you put the spackle on it, it covers up the hole. Spackle. Electronic spackle. All right. So this would be 3 phase, 6 pulse, which, you know, you got 3-phase, 6 pulse, 12 pulse. And I gotta talk about the, you know, how all that happens, but at any rate, you got 3-phase, our voltage ripple never comes to a stop. It never ends, right? So what that means is that our average energy, you know, if we've taken away all these minimum test scores through here, then our average is going to go up. What controls minimum energy? The only thing that controls minimum energy is, the only thing that controls maximum energy is KVP, right? So those two are off the table. So then machine phase, though, what we get is that doesn't look anything like that one. All right, so with machine phase, then what we get is an increase in output. Instead of having 1 pulse, we're going to have 3 per, possibly, you know, twice as many, but at least 3 pulses per, you know, per pulse. So when we rectify it, we get 6 pulses. All right, so we get output. We get an increase in output, but because these represent voltage, not maximum voltage, but they still represent voltage, and we've eliminated the minimum voltage, then what's going to happen to our average? And we just said it already, it's going to increase. So what does this represent? Average, right? So what we're going to get is an increase in output. Peak energy doesn't change. We get an increase in output, it pushes towards the high energy side. Increase in numbers pushes towards the high energy side. Okay, where you're going to confuse these two is the similarities. When we change from single phase to 3-phase, we get a increase in average. Maximum energy doesn't change, right? So we get an increase in average, we'll get an increase in output, and then you're going to flip that around to filtration, or you're going to go from filtration to 3-phase. And because the average energy increases and the numbers change, you're going to have a tendency to conflate the two. Okay. With filtration, we're going to get a decrease in numbers, and that's the part of this that you're going to have a tendency to, you know, to mistake on the test. With filtration, you're going to get a decrease in numbers. With machine phase, you're going to get an increase in numbers. So, walking back through it, if you increase filtration, what are you going to have to do with your technique? Because you get a decrease in numbers,
Increase mass.
you're going to have to increase mass, right? You go from a single phase to a 3-phase, and because you get an increase in numbers, you're going to have to do what? Decrease mass. And this also is where you're going to trip up a little bit. You're going to have a tendency to say, okay, I had single phase, now I got 3-phase. I'm going to have a tendency to go, well, I've got 1 to 3. It's a factor of 3. It's going to be a factor of 2, right? So if you go from a single phase to 3-phase machine, you get an increase in output. You need to decrease your mass by a factor of 2. It's about 2.5 for high frequency. But if you go from a 3-phase to a single phase, you're going to have to increase by a factor of 2. Right? So both of those are going to be mass. Those are the only two. Distance. Yeah, distance. So SID, changes in SID. So this is compensation for changes, right? So with the change in SID, excuse me, does not affect your Brems spectrum at all. Right? Just the presence of an increase in SID does not affect your Brems spectrum. If though you want to maintain your exposure, then you have to change your mass, and that comes into play, right? So if you change your SID though, let's say you go from 40 to 72 inches, what do you got to do?
Increase your technique.
Increase your technique, specifically
Mass.
mass by a factor of 3.2. Very good. 3.25, 3.24 is, technically it, but 3.24, right? Go from 40 inches to or 80 inches, then you need to change it by a factor of 4, double, right? So, any questions on that? So this question kind of trips people up a bit. Make sure you understand the question as you increase your SID. If it doesn't ask you for, what do you need to do with your technique? If you increase your SID, what does it do to the Brems spectrum? Nothing. If you increase your SID and you don't adjust your technique, what's it going to do to your image receptor exposure? Decrease it. Now, some of the text and even some of the test questions, some of, the wording in my PowerPoints really need to be updated. I still spit out changes in density. And this is the reason that you're going to get that referred to, by some of your older texts, is if you increase your KVP, traditionally, as you increase your KVP, you get all this change. And especially where you're going to get an increase in numbers is post-patient. If you increase your KVP and that's all you do, then what would happen with your screens and films is the screens glow brighter, expose the film more, and you would get an increase in density. Increase mass, glow brighter, increase in density. Change from single phase, 3-phase, glow brighter, increase density. Increase filtration, glow dimmer, decrease density. Okay. So if, you hear density, that's what they're referring to. Now it's exposure. Increase KVP and do nothing else, then your S number reflects an increase in exposure. You increase mass, overall mass, and you change nothing else, increase in image receptor exposure, your index number is going to represent that. Change from 3-phase to single phase, you get a change in your S number. In that case, it indicates an image receptor exposure. Decreases, increased filtration, same thing. Okay? That's where we'll be, for the lecture next week too. Is just looking at it and working through it all the time. Any questions?